Alright, we're going to look at acceleration. Acceleration is the rate at which velocity changes with time. Now, to change velocity, things we have to remember is we have to remember the velocity changes when the speed of the object changes. So when we change the speed, velocity changes, or when the direction changes. So a change in velocity is either a change in speed or a change in direction. Therefore, acceleration occurs change in speed or a change in direction, or obviously a change in both. So here's an example. Okay, our cyclist is speeding up right here. He's going, in 1 second, he went from 0 meters per second to 2 meters per second. He accelerates. And then you can see this acceleration stays constant throughout. He is, for every second that he travels, he goes 2 meters per second faster. So here's a toy car moving along a track. There's like snapshots taken at 1 second intervals. Green arrows indicate the velocity at each instant. The car is, the longer the arrow, the greater the speed. So as the car goes through here to here, the arrows will get progressively longer. When he gets to the bottom, you can see the arrows have a pretty constant shape, which means they're going to the same velocity. Then as they go back up, they slow down. Okay, so in what section does the car accelerate? Accelerates as it's going down and accelerates as it's going up. That's where the arrows change shape. Now, normally our body cannot detect constant speed or velocity, but it can sense when we speed up. For example, if you're in a car, you might feel the seat pushing forward on you when you speed up. When you slow down, you have the seat belt that's pulling you back down. And then you definitely it should be lean to one side when the car rounds a corner. So when you go around a corner, you feel the lean of your body. That is a change in direction. So acceleration can be in a car, the forward pull, the seatbelt pulling back, or when the car turns, we feel the motion. Can change in direction or change in speed. Formula for average acceleration is change in velocity over change in time. Final velocity minus initial velocity over change in time. When we talk about units, the units are velocity units divided by seconds. So meters per second is what we use normally in the metric system. But it can be meters per second per hour, kilometers per hour per second. It's just going to be a distance in 2 time units when we see it. You can see some typical accelerations. You can see the bullet fired from a rifle, a batted baseball, if you're watching the Little League World Series right now. And then, of course, acceleration in an elevator, stopping of a car, etc. But you can see the different numbers and how they relate to meters per second squared. So, advertisement says a car can go from 0 to 26.8 meters per second in 6.2 seconds. The question is, what is the average acceleration? Acceleration is final velocity minus initial velocity over change in time. My final velocity is 26.8 minus 0 over my change in time, which is 6.2 seconds. So 26.8 divided by 6.2 gives me an acceleration of 4.3 meters per second squared, or meters per second for my velocity, and then divided by seconds for my time, meters per second squared. Oh, sorry. Part B. Drag racer deploys a parachute, slows down from 130 meters per second to 45 meters per second in 3 seconds. What is the acceleration? Again, acceleration, final minus initial. My final velocity is 45 minus my initial, which is 130. Divide that by my time of 30 seconds. I get 45 minus 130. And I divide that by 30. And I get negative 28.3, same units, meters per second squared. So I see this now. Negative and positive, negative acceleration and positive acceleration can occur. So you got to keep track of your directions there. We determine it graphically. If we have a velocity time graph, right here, the slope is our acceleration. I repeat that. The slope of a velocity time graph is the acceleration. So here's velocity time graphs for two different cars. They're both accelerating because we have a positive slope. Is the acceleration of car A greater than, less than, or equal to that of car B? Well, we can just eyeball it and see that A has less slope than B. Therefore, A is not accelerating more than B. But an important point to make here is A is still going faster than B at the end of our graph. It has a greater velocity. It's just B is catching up because B is definitely accelerating faster. So, subway train speeds up an acceleration of 1.2 meters per second squared. How much time does it take for the train's speed to increase by 4.1 meters per second? So, acceleration. Change in velocity over change in time. We don't have to worry about our final initial velocities. We just know the change is going to be 4.1. We're trying to find delta t, knowing that our acceleration is 1.2. So we do our magic math here. Change in time is equal to 4.1 over 1.2. Got my numbers transposed, but 4.1 divided by 1.2. So we take our change in velocity over our acceleration, and we get 4.1, and we divide that by 1.2, and we get a time of 3.4 seconds. So that's how long that would take. So we can use this equation to find other things other than just plain acceleration. So the speed of an object increases when its velocity and acceleration are in the same direction. This is very important. So if velocity is going in the positive and acceleration is going in the positive, we are speeding up. If velocity is in the positive and acceleration is in the negative, we are slowing down. And here's our two graphs. When we speed up, we have a positive slope. When we slow down, we have a negative slope. Let's look at it in another way. Positive and positive, speeding up. Negative and positive, slowing down. Let's look here. We're going in the negative direction, but we have a positive acceleration. We are slowing down because the signs are opposite. Once again, here, acceleration and velocity are both negative. That means we are speeding up. So when we look at a velocity time graph, if the line is like B or A at the bottom, going towards 0, we are slowing down. If it's going away from 0, we are speeding up. That's important to understand about graphs. So let's take a look here. Which lines indicate slowing down? Which lines indicate speeding up? Anything going towards 0 is slowing down. So let's look at 1. 1. Going towards 0, slowing down. 2. Going towards 0, slowing down. 3. Going away from 0, speeding up. 4. Going towards 0, slowing down. So which ones are slowing down? 1, 2, and 4. 3 is the only one speeding up. Here's a problem. Ferry makes a short run between two docks, one in Anacortes, Washington, and the other on Guaymas Island. The ferry moves in the positive x direction as it approaches Guaymas Island with a speed of 7.4 meters per second. If the ferry slows to a stop in 12.3 seconds, what is the average acceleration? So A, acceleration. Velocity final minus velocity initial over change in time. My final velocity, it's slowing to a stop, is 0, minus my initial velocity of 7.4, divided by my time of 12.3. So we're checking this out, and we say negative 7.4 divided by 12.3, and we get an answer of negative 0.60 meters per second squared. Again, negative because we are slowing down. If the ferry returns to the dock with a speed of 7.3 meters and it comes to rest in 13.1 seconds, what is the average acceleration? So we'll go in the opposite direction now. Okay. So returns to the dock. So we're going to the negative direction. Okay. So we're going to go negative 7.3. Right? Or I'm sorry, 0 minus negative 7.3. Over our change in time of 13.1, what do we get? Well, these two negatives make these positives, so it's 7.3. 7.3 divided by 13.1, both positive. and we get an acceleration of 0.56 meters per second squared. Positive, again, slowing down because we're going in the negative direction. Positive acceleration means we're slowing down. In A, we're going in the positive direction. Negative acceleration means we're slowing down.